तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
In the last class, we solved example 7 and example 8. In example 7, VBE comes out as how much? 0.538 and not 0.63, okay, as indicated earlier. So, please make this correction, and accordingly the other values will be adjusted. So, please calculate. In example 8, I asked you to find out R1 and R2, okay, for biasing, and that comes out as R1 equal to 35 K and R2 equal to 140 K. So, these are the answers which you should have obtained in your hostel while calculating. All these problems you must work out, okay, and see whether these values are correct or not. So, we will continue further with discussion about transistor amplifier. We had discussed transistor biasing. We know how to bias a bipolar junction transistor so that it is in the active region, and we also know how to bias it in a stable fashion. Right? Now, some variations in this. We have put in general a resistance through a supply voltage R1, R2. This is the generalized way of biasing that we had discussed. Now, how to feed a signal is what we are going to discuss for this amplifier. So, we have a general scheme using single supply. We have another scheme using dual supply. These are stable ways of biasing. Both these schemes we had discussed. In this scheme of single supply, we had to use additional resistances R1 and R2. In this, we are using only two resistances. So, let us discuss both these schemes. This is single supply dual supply. In single supply scheme that we had discussed, we saw that this can be equivalent to RC, VCC, RE, RB, and VB, where VB was equal to VCC into R1 by R1 plus R2 Thevenin's voltage, and RB was equal to R1 R2 by R1 plus R2, parallel combination of R1 and R2, and we had designed it in such a manner that beta plus 1 times RE is much greater than, okay, RB. For fixing the emitter current, in both the circuits emitter current is getting fixed. In this it automatically gets fixed. Okay. In this, only when this condition gets satisfied, it is the emitter current gets fixed as, in this case, VEE minus V gamma divided by RE. In this is going to be VBB, okay, minus V gamma by RE. So, this is how the emitter current gets fixed. What happens is the drop across RB, which is IB into RB, is small compared to IE into RE. That is what gives this formula. So, with this knowledge about biasing, we would now like to see how signal can be applied to the transistor. So, how do we apply signal? Signal, as we know, is a time varying component which we would like to amplify. Okay. And let us consider this circuit first. In this we had grounded this, output can be taken from here, no problem. I want this to appear as a common emitter amplifier. This is no longer, as far as DC is concerned, this is not a common emitter configuration, this is a common base configuration. Base is common, right? The potential with respect of the base is 0, and potential of every other terminal is measured with respect to the base here. So, base is common. I want it to, as far as signal is concerned, to appear as common emitter. I want to apply the signal still between emitter and base. So, the emitter is with respect to DC lifted, right, but I want it to be grounded. So, for this purpose we use what is called a bypass capacitor. The capacitor for signal will act as a short circuit. For signal, capacitor acts as a short circuit. This is called bypass capacitor. Short circuit compared to what? This is an important concept. This is grounding it, right? That means potential across this, as far as AC is concerned, is 0. That means this has to be compared with something that comes in series with it. We want the potential to appear between base and emitter terminals, base and emitter terminals. That means the entire input potential, which I am going to apply here now as signal, This is the signal source. This is signal source is assumed to appear between ground and this terminal, right. Now, this base is directly connected to the other end of the source. So, signal it might have a source resistance, does not matter, is directly coupled. So, here signal source is directly coupled. This is called direct coupling. Since the base current is very small, the base DC current is very small, in this case direct coupling may be allowed, because source may tolerate that small amount of DC current flowing through it. Then I can directly couple the source. So, base is connected to one end of the source, the other end of the source is grounded. So, this has to be grounded with respect to what? Base to emitter junction. So, whatever drop occurs here, that should be large compared to drop occurring across the capacitor. So, the capacitor is a short circuit compared to the impedance level that is occurring here. The impedance level that is occurring here is nothing but Re, small re. Right. So, the capacitor should be very small, that is capacitive reactance should be very small compared to Re. That means Re should be much greater than 1 over 2 pi f into C. This is the capacitive reactance, Ce. If you assume that for small signal the resistance between base and emitter can be replaced by Re, what is Re? Re is Vt divided by Ieq, which is nothing but delta Vbe divided by delta Ie. This we had already discussed earlier. Delta Vbe by delta Ie, small change in input voltage Vbe divided by small change in current, which is defined as small signal resistance at the emitter, Vt divided by Ieq, where Vt is equal to 26 millivolts at room temperature. So, this is a useful design equation. So, the bypass capacitor, please remember, is bypassing what? This path which the current would have taken. The current now takes this path, right? And the current is going to be determined mostly by this impedance, because this is negligible, reactance is negligible compared to this impedance here, Re. So, this is something that I want to point out, that you have to worry about this impedance while evaluating the value of the capacitor needed to act as a short circuit. Even though it is bypassing the capital Ra is going to be very large compared to small re. For signal, you have to make this a short circuit compared to small re, which is going to be of the order of tens of ohms. Okay. So, Ce therefore is going to be chosen to be much greater than this 1 over 2 pi f into R. At the worst case is corresponding to the minimum frequency, if you design minimum frequency of use of this amplifier. Let us say signal minimum frequency that you want to amplify is 100 hertz. then f minimum is 100 hertz. Above 100 hertz, it is automatically getting varied, right. So, this equation is automatically getting varied. So, you have to design it for the worst case, that means for the minimum frequency it should still appear as a short circuit compared with what? Small Re. So, selection of the bypass capacitor is very, very important. How do you do the measurement in the lab? Okay, you have the voltage that you can measure with respect to ground, measure the base voltage with respect to ground, okay, and measure the emitter voltage with respect to ground. Emitter voltage with respect to ground should be very nearly 0 compared to the base voltage. That means, most of this voltage, source voltage, is appearing between base and emitter. Okay. So, if this is done, this is a good way of bypassing the circuit. It is assumed that Rs itself is going to be very small. So, that the source voltage is very nearly same as the open circuit voltage here, Vs. Now, the actual equation requires that the Ce is so chosen that the reactance of Ce is small compared to the impedance coming across it. This is like any other design that we had discussed earlier, the coupling capacitor also. Any capacitor is chosen, okay, bypass or coupling in such a manner that 1 over 2 pi f minimum Ce, that is the reactance, is, okay, much less than, okay, the resistance across what? Ce. Now, let us see whether we have done it properly. Resistance across Ce is this resistance to ground, this is one resistance to ground, that is capital Re. This resistance is coming from here to ground. Then from here to ground you have to trace the path. So, capital Re parallel small Re, this resistance small Re, from here to here we have come. And if the source is having resistance, then that Rs, okay, divided by beta plus 1. Why? You can see, if the current here is unity, emitter current is unity, capital Re will come. The current in this is beta plus 1 times less. So, whatever impedance is there, okay, its drop is also going to be beta plus 1 times less. Okay. So, the current in this and current in this differ by beta plus 1. So, any impedance here can be transferred to this side as Rs divided by beta plus 1. So, the effective this thing capacitor should be such that its reactance is very small compared to capital Re parallel Re plus Rs by beta plus 1. Then why did we take this? That is because beta is normally very high and Rs itself is very small. So, this factor is normally negligible. Then capital Re is going to be very large compared to small Re, and therefore, this parallel combination itself results in Re. So, normally, right, this design is going to work properly here for selecting. Otherwise, if this approximation cannot be made, then you use the expression Re parallel capital Re plus Rs by beta plus 1 as the actual resistance for fixing up the value of Ce at the minimum frequency of interest for the amplifier. So, we will once again discuss about this impedance levels later, okay, while evaluating input impedance, output impedance, etc. But please remember that what we are seeing is the impedance seen from here. The impedance seen from here is going to be this resistance to ground, because battery is going to be short circuited, okay, because there will not be any delta VEE by delta IE change, because this is a constant source. So, this will be grounded. As far as AC is concerned, this will be grounded. Then this is going to be replaced by Re, and this resistance, because it has beta plus 1 times less current than this, is going to be replaced by an impedance which is Rs by beta plus 1. So, this is an important design criteria for fixing the value of the bypass capacitor Ce. Now, I have made this a common emitter amplifier by biasing it properly, fixing the emitter current and grounding this emitter point as far as signal is concerned using the bypass capacitor. After we do this, let us see what happens when we now apply this signal Vs. As far as the signal is concerned, now I can put down the equivalent circuit for this as Rs, Vs, then it comes to the base, then this base point is going to be replaced, let us say, by small Re, which is nothing but delta Vbe by delta Ie. This is the equivalent resistance between the base and emitter is going to be, and emitter is now grounded through the bypass capacitor. So, the entire signal picture on this side of the loop is just going to look like this. Now, as far as this side is concerned, this junction, if this is delta Ie current, let us say delta Ie, then this current is going to be alpha times delta Ie, which is the transistor equation, because we know that Ie is into Ic is equal to alpha times Ie, okay, plus Ic naught. So, delta Ic by delta Ie is equal to alpha here. Ic naught is a constant current, right. So, delta Ic by delta Ie also is called alpha, right. So, alpha is the current amplification factor which we have discussed, which is very close to 1, typically of the order of 0.99, 0.995, etc. So, we have this current flowing through this like this, then we come to the collector, and from the collector we have a resistance to ground. This is what is called equivalent circuit for this common emitter amplifier. Once again, let us trace this. Vs is replaced by Vs signal, Rs is Rs. This is a small signal, okay. So, strictly speaking, I would put it as, right, we will put it as delta Vs, indicating it is small signal. So, corresponding to which we have replaced this transistor by delta Vbe by delta Ie, so Re, and that delta Ie is supposed to flow through Re, okay, resulting in a collector current of alpha times delta Ie from this relationship, and this whole thing is an equivalent circuit. This is the simplest equivalent circuit one can think of for the transistor. Now, we will find out what is this current that is flowing through the input of the transistor, which is called delta Is. Let us see. Let us find out from this. I know that this is delta Ie and this is alpha times delta Ie. So, what is this going to be? This is delta I, this alpha times delta I. So, what will be this current? Okay. So, delta I has gone over this and this is delta alpha times delta I. So, this will be 1 minus alpha times delta I. Is it clear? So, that this plus this comes out as delta I. So, this delta I subtract this alpha times delta I from that, then will be the resultant current in this 1 minus alpha times delta I. So, delta IS is equal to 1 minus alpha times delta IE from the Kirchhoff's current law. And what is delta IE? Okay. If this is a voltage here, delta VI, we will call this delta VI, the voltage between base and ground directly at the input of the amplifier. So, delta VI is equal to delta IE into RE. This delta VI voltage across this is nothing but delta VI into RE, delta IE into RE. So, what is delta IS? 1 minus alpha times delta IE. So, we can represent this as RE, okay, and delta IE can be replaced as delta IS by 1 minus alpha. So, in this loop we can therefore write as delta Vs, which is this voltage, is equal to delta Is times Rs, delta Is times Rs, plus this drop, that is the Kirchhoff's loop equation, okay, delta Is by 1 minus alpha times small r. So, you can see that delta Vs by delta Is, okay, effective resistance seen from here is nothing but Rs, okay, plus Re by 1 minus alpha. That means, it is the original Rs through which delta Is flows, and this Re which is there between base and emitter appears as Re by 1 minus alpha. Okay. So, that is called the input resistance of the amplifier. So, when I connect a source with a source resistance of Rs, from that source, okay, a current that flows, that is determined by an impedance which is Rs plus Re by 1 minus alpha. So, what this amplifier is going to offer as impedance is Re by 1 minus alpha. So, input resistance of the amplifier is nothing but Re by 1 minus alpha, or is equal to Re into, I told you alpha is beta by 1 plus beta. If you replace it by that, beta by 1 plus beta, you will get this as Re into 1 plus beta. So, as far as common emitter amplifier is concerned, the input impedance is Re into beta plus 1. Okay. Now, as far as the output voltage is concerned, let us check. Output voltage is going to be how much? Rc into current which is alpha times delta IE. This is equal to minus delta V naught, because current is flowing this way, right, and I have assumed delta V naught is positive this way. So, minus delta V naught is Rc alpha delta I, or delta V naught is equal to minus RC into alpha into delta IE. Okay. Delta IE is nothing but delta VI divided by RE. So, from this is delta VI, that divided by RE is delta IE. So, now from this you can get delta V naught by delta VI as equal to minus alpha RC divided by RE. Very important equation. Alpha is very nearly equal to 1. So, essentially the gain of the amplifier delta V naught by delta VI is alpha RC minus alpha RC divided by RE. RE is already known, okay, as VT divided by IEQ. Okay. So, the gain of the amplifier is minus, indicating there is an inversion. If the input is increasing, output will be decreasing. There is an inversion. This also we had discussed earlier for a general amplifier, and its value is minus alpha RC divided by RE. What is minus alpha by RE? This is called, alpha by RE is called GM, transconductance of the amplifier. This also we have defined, delta IC divided by delta VBE. Okay. Delta IC divided by delta VBE is nothing but delta IC divided by delta IE, okay, into delta IE by delta VBE. Delta IC by delta IE is alpha, delta IE by delta VBE is 1 over RE. So, this is nothing but alpha divided by RE, which is called the transconductance GM of the transistor. So, this gain is equal to minus GM RC. This also earlier we had discussed. Okay. So, we have now obtained the input impedance of the amplifier, output, the gain of the amplifier, output divided by input, and what is the output impedance? Seen from here, okay, since there is a current source, output impedance is infinity in this case, right, from here. So, if it is an ideal current source output, then obviously output impedance is infinity. If of course there is a high resistance between this and this, okay, indicating some leakage resistance, okay, between collector and base, okay, it is having a leakage resistance, then of course there will be finite output impedance. So, it is enough if we learn this basic thing about the common emitter amplifier. Its input impedance is going to be small RE divided by 1 minus alpha or RE into 1 plus beta, and its gain is G minus GM into RC. So, let us now take an example to illustrate this. Example 9. Design a common emitter amplifier to operate at IEQ equal to 1 milliampere, VCBQ equal to 5 volts, and VCC equal to 10 volts, VEE equal to minus 10 volts. Then obtain the voltage gain and input resistance of the amplifier. So, let us continue with the example 9. We have here the pictorial representation of the same amplifier with biasing scheme using dual supplies, plus 10 volts and minus 10 volts, connected through RE to emitter, connected through RC to collector, connected through RS the input signal to the base, emitter grounded. So, it is grounded emitter amplifier. Now, bias current IEQ flows through this RE, it cannot flow through the capacitor. So, it is the same current here as well as here, and that has been specified as 1 milliampere. Okay. This voltage VBEQ is not given, but we can, whenever it is not given, we can take it as equal to 0.6 volts. This we know. So, this is 0.6 volts. So, nothing has been mentioned about the source and all that. So, as far as this is concerned, we will consider that the source is being fed here, but for the time being we do not know anything about RS. So, we will assume RS is 0. Okay. The source is going to be connected here. So, basically we have, as far as DC is concerned, this having 0 DC potential, otherwise the base current will also flow through the source resistance. So, please remember, if the base current is IB, then this, if there is direct coupling, then through RS the base current will flow. So, in an actual situation you will see that this potential is going to be IB into RS DC potential. If the source resistance is not given, nothing is mentioned about it, we will assume RS is 0 and this is grounded. If source resistance is given, then we have to consider this DC drop along with 0.6 also. Okay. So, how do you know this drop? If you know the beta of the transistor, let us take beta is assumed to be about 200. Okay. Then this IB into RS is same as, okay, IE divided by beta plus 1. IB divided by beta, IE divided by beta plus 1 is IB into RS. So, IE is given as 1 milliampere and RS may be known, let us say 1 kilo ohm. So, suppose RS is 1 kilo ohm, 1 milliampere into 1 kilo ohm. Okay. So, that is going to be about 1 volt drop. Okay. So, that divided by beta plus 1, which is about 201. So, 1 volt divided by 201, okay, which is negligible. It is about the order of 5 millivolts. Okay. This itself has been assumed at 0.6. This is not 0.6. This may be 0.625 or some 638. So, there is no point in considering this drop at all, and therefore, normally under normal source resistances of the order of kilo ohms, this is negligible. If it is not negligible, take it into account. Okay. It should become comparable to 0.6 volts. Okay. Then only you need to take into account. So, otherwise this is always negligible. So, this is going to be almost at DC ground potential, okay, under normal circumstances because of this exception. So, the base is going to be still at DC ground potential. This is 0.6, this is 5, okay, and therefore, the current in this is going to be 10 minus 0.6, okay, divided by RE. If this is at, let us say, some potential which is IB into RS, then that IB into RS should be added to 0.6. Otherwise, it is 10 minus 0.6 divided by RE. So, in this loop, the DC drop, AC signal is 0. So, the DC drop, quiescent drop, when the signal is not there, is 10 minus 0.6 divided by RE, that is to be made equal to 1 milliampere. So, RE equals, okay, 9.4 kilo ohms. So, RE has been now fixed to make the IEQ equal to 1 milliampere, given this voltage is 10 volts. So, even in a general situation where RS is given, right, you have to verify whether this is true and make this assumption that this is negligible compared to 0.6, right. Okay. Then this is at 10 volts, okay, and this is very nearly at the ground potential, and therefore, this is very nearly from the ground equal to 5 volts. This is given because VCB is given as 5 volts. So, if this is at 5 volts, then the drop across this RC is 5 volts. So, drop across RC, which is ICQ into RC, is equal to 10 minus 5, which is 5 volts. So, RC is equal to 5 volts divided by ICQ, which is very nearly equal to 1 milliampere, we can assume. It is alpha times, okay, 1 milliampere. Alpha is going to be 0.995 because beta is given as 200. So, alpha is going to be 0.995. So, we can assume that this is F3 equal to 5 kilo ohms. Is this clear? So, we have RC also fixed now as 5 kilo ohm and RE is fixed as how much? 9.4 kilo ohms. Then CE 1 over 2 pi f min into RE. Okay. CE should be much greater than this according to us. Right. We can again check. RS is assumed to be 0. If RS is not 0, then we have to compare with RE plus RS divided by beta plus 1. Okay. Parallel 9.4K. Anyway, RE is going to be of the order of 26 ohms because 26 RE is 26 divided by IEQ, which is 1 milliampere. So, it is equal to 26 ohms. So, should be greater than 1 over 2 pi. Let us say F minimum, we will take it as, if it is not given, right, let us say we are going to fix it as, let us say 200 hertz, something. We are not interested in any frequency less than 200 hertz. So, this into 200 hertz into 26, okay, farads. So, can somebody quickly evaluate how much this is? 2500 for, so 4 pi. $30? Again, all of you verify, right? So, much greater than 30.6 microfarads, about 300 microfarads is the typical value, okay, for this kind of frequency, right, wherein this capacitor is going to act as a short. Okay. So, it is enough if we take 3E equal to, let us say, 300 microfarad. So, we have now designed a nice common emitter amplifier, okay, which we can use. Now, let us see its performance, right, factors. What are they? Input impedance and gain. So, let us, we have made it work beautifully in the active region by biasing it at 1 milliampere and VCB equal to 5 volts. Okay. It is in the active region, that we have made sure of. Whatever be the transistor that we put here, the bias point is not going to get altered. That is why it is called stable operating point, that we had assured, right. And now we can see its performance, Ri, input impedance, which is equal to delta VBE divided by delta IB, because delta VBE is the input signal here, okay, delta VBE. This is 0 drop from here to ground, emitter to ground, it is grounded. Okay. So, delta Vi is going to be added to this as delta VBE. Okay. So, delta VBE by delta IB, that is the input impedance, which is equal to delta VBE divided by delta IE, okay, into beta plus 1. So, delta IB and delta IE are related by this factor beta plus 1. Delta VB by delta IE is nothing but Re. This is what we had done earlier also, Re into beta plus 1, and Re is 26 ohms into 201. So, this is equal to 26, 52, 5.226 kilo ohm. Okay. This is the input impedance resistance of our common emitter amplifier. Now, delta V naught, which is going to be taken here, divided by delta Vi is going to be equal to minus alpha Rc divided by Re, okay, which is going to be minus 0.995 into Rc, which is 5 kilo ohms, divided by 26. It's about 200, right? How much is it? Please calculate. This is about 200. 191. That is the voltage gain. So, we have worked out all the performance factors of the amplifier. Now, let me just tell you something more about this amplifier so that it is clear. When the signal is fed, okay, this is going to be the signal, let us say delta Vs. Okay. So, the potential here is going to be changing by delta Vs, okay, above the ground. Further, there will be through this IBQ flowing, okay, and then there will be delta Is flowing, okay, IBQ plus delta Is flowing. Right. So, IBQ is the quiescent current. Here we have ICQ flowing. Right. So, this is 10. So, 10 minus ICQ into this thing, this is very nearly equal to 5 volts, okay, VCQ. So, around 5 volts you will have this plus delta V naught. Okay. So, this 5 volts is the quiescent output voltage. Around this 5 volts, okay, delta V naught is going to be available. If this voltage increases by some amount, this voltage will decrease. Let us assume that this is a sine wave. So, this point is very nearly at about 1 to 2 millivolts quiescent, that we have found out, okay, for RS of the order of kilo ohms. Okay. So, it is very nearly at ground potential, and then it is going to change in this manner. What is this? This is the delta Vi. So, this is delta Vi. So, delta V naught is going to be about 191 times, okay, delta Vi, but with a negative sign. What it means is, it is going to be amplifying it, but it will be negative, that means it will be decreasing, and it will be 109 times amplified. Right? This is not to scale, this just indicate that this is how it is going to look like. This is the quiescent situation 0, and if you plot this also around 0, the output, this is how the output will look like. But this output will be on a pedestal of 5 volts. Suppose therefore, delta Vi is of the order of, let us say, 10 millivolt peak. So, this is 10 millivolts. Then this will be 10 into 191, that means this will be 1.91 volt around 5 volts. So, the quiescent state of this output will be around 5 volts, and it will be decreasing like this and going like this, and 1.91, that means 5 minus 1.91 is this point, and this point is going to be 5 plus 1.91 volts. That means this will be 6.91, and this will be 904, 4 point, is it correct? 3.09 volts. So, that means output will change now in the same manner as the input, as long as the input is a small signal, and it will be proportional to the input, but there will be phase shift. So, if the input is sinusoid, output will be also a same sinusoid with a phase inversion, but it is going to vary from this value to this value. When this is happening, right, this voltage here is going to decrease. Up to what value can it go on? It can go on until this voltage becomes equal to 0. This I have told you. VCB equal to 0, it is entering the saturation. Okay. That means this signal, if you keep on increasing, this signal will keep on increasing, and this point will be coming towards a point where this voltage is nearing 0. This is already close to 0. Then VCB is going to be 0. Then the transistor enters saturation. On the other side, what is happening? This is going on increasing. Up to what point can it go? Why is it increasing? Because the instantaneous value of the current here is decreasing. Okay. Why was it decreasing? Because the instantaneous value of current was increasing. This ICQ was becoming equal to plus delta IC, right? And this delta IC was increasing so much that this was going to saturation. When this is decreasing, this delta IC can become at most equal to minus ICQ, so that this current is 0. Then the transistor is off. Instantaneous value of collector current is 0. So, the voltage will be 10 volts. So, this will go up to 10 volts. This is now gone to 6.1. This can go up to 10 volts. At that point, the transistor is cut off because IC is 0. So, there are 2 points. IC, instantaneous value of IC becomes equal to 0. That is called what? Cut off. Transistor is cut off. And here what? This will go towards saturation. what is saturation? Instantaneous value of VCB is equal to 0. So, please remember this, our amplifier is able to follow the signal increase or decrease only up to these 2 points, where instantaneous value of collector current is 0, that is called cutoff, and where instantaneous value of collector base voltage is 0, which is called saturation. Now, the question that I am asking is, what value of signal output, okay, will this go to saturation? It is very easy, because we have selected VCBQ as 5 volts, the maximum it can have is 5 volts, right. That means this swing here on this side can go as much as 5 volts. Okay. So, important thing, if you want a swing of 5 volts, select VCBQ of minimum equal to 5 volts. Okay. Then the swing also is governed on the other side by ICQ. So, if ICQ is chosen as 1 milliampere, then for it to become an instantaneous value to become 0, delta IC should become 1 milliampere. That means the swing on the other side is 1 milliampere, that is ICQ times RC, right, which is in this case 5 volts. So, in this design I have chosen purposely a symmetrical swing, that is when it goes to saturation, it is also going to what? Cut off. So, the operating point has been intelligently chosen here, so that it is having symmetric swing of 5 volts both on the positive side as well as the negative side. This will be distorted, because the linear relationship between input current and output current, okay, is linear, but input current and input voltage is exponential. So, this waveform will not look like a sine wave at all when you have this much swing, but it can swing by that amount, okay, for a specific swing at the input. If you can swing the input correspondingly, right, then you can go to saturation and cut off here. The waveform will not look like sine wave any longer because of the non-linearity of the amplifier. So, you can therefore always locate the operating point in such a way that this symmetric, okay, swing limits get reached, okay, if you are amplifying sinusoidal signals, right. If you are amplifying some other type of signal, then depending upon the positive and negative going signal, right, you can accordingly select the operating point, so that it is all the time, okay, in the safe range of operation.